Yeah, so it'll start not with this stuff, but when you get to this part. Is that what you meant?
Yeah, that's what I was wondering.
Yeah. So whenever you start seeing capacitors, that's when it comes in. All right. Concept tests are a good thing to look over. Your tutor is good to look at too. We can look at some of those if y'all have particular problems. But first, I just want to show you the 4 free response. Just review those again, give you some flavor for that. We've been doing that all along, but just to remind you, we'll have 4 free response. The first one will be a capacitor circuit. And it's going to be one of those where they're laid out not normal, right? So something like this one, for example, where you have capacitors that are laid out not sort of in the standard grid or with the standard where the parallel branches are obvious to you, but where it maybe is not so obvious. So we can look at some of these in just a minute. The second one will be a multi-loop. Kind of like the ones that we worked in class yesterday. It'll be an easier, it won't be a whole system of equations that you have to solve. You'll be able to set it up so that you can solve it with a simple one-step equation. But you'll have to know how to write the equation, know how to label the currents, know how to interpret the directions that you travel in the circuit. We can look at that. The third thing will be a combination circuit. And in the combination circuit, it'll actually be 2 problems. So like you'll see question number 3 on the page right here. So like you have question number 1, question number 2, question number 3, and then way down at the bottom you have question number 4. And so with question number 3, I'll ask you, what is the equivalent resistance? And then I'll also ask you, which is really going to be question number 4, what is the voltage or current in any one of the resistors? And so you'll work number 3. Here will be your circuit right here. And you'll work number 3, and then you'll just show your work for number 4 right there alongside it. You know, that's all I'm saying. It's going to be 2 questions. You'll work it all as one. I'll just be asking you for 2 different values. The equivalent resistance, and then also the current or voltage on any one of the resistors. We've done a bunch of those, but we'll do some more today if you like. And then there will be 20 multiple choice questions. One of those is a gimme, just for the version number, and the others will be mostly conceptual, though there are some calculation problems. Like, for example, there's one of those problems where you have to find the resistivity of the unknown metal. We did one of those in class. I told you you'd have it on the test. There will be some about like where you're changing the dimensions of your capacitor or the dimensions of your resistor and how does that affect various things. There will be questions about circuits where you have, I asked you, what is the voltage on a particular resistor? But they'll be simpler than the ones that you do in the free response. Fewer resistors, fewer capacitors, more simple layouts. So you should be able to do those without going through all the steps. If you're not able to do that, that's fine. Like if you have to go through the steps, that's okay. But if you've been tracking along all this time, then you should just be able to look at those circuits and say, oh, the voltage is blah, without much work. Okay? All right. You want to look at capacitor circuits first? Is that okay? So let's look at this one. This one is a good indicator of something that you'd have. It'd be something similar to this. Not identical to this, of course, different numbers, different layout, but something similar. The first thing that you want to do is just to redraw the circuit, or you might not have to redraw the circuit, frankly. You might be able to see that this is a parallel branch and this is a parallel branch. You might be able to see that. What you want to look for in this is you start at the battery. So I start right here, and then I go along until I come to a junction. That's my first junction. And then I realize that that junction has 3 parts to it. 1, 2, 3. The reason I know it has 3 is because, well, this breaks and goes to another capacitor, this goes to another capacitor, and this goes to another capacitor, but there are no other capacitors in between. So I could redraw this circuit where I have my 12 volt like this. So that's my 3, 3, 6, and 6 microfarad capacitors. And then those all come back together. And I recognize that when I have a construct like that, that I could collapse that all down to a point and just get rid of that line. It comes back together, and then it breaks again into two parallel branches. I have to be careful here because this is a single series, or it's not even a series because there are only one capacitor, but that's not like a third parallel branch, even though there's a bend in that wire. So this is my circuit. I have a 4, 4, and 2. Then I would find the equivalent capacitance. I would start with this and this. A 3 and 6 in series. That's 1 over 3 plus 1 over 6. That's equal to 2. And then a 4 and 4 in series. Let's see, that's also equal to 2. So both of those are equal to 2 microfarads. So then I can redraw again. You might be to the point where you don't have to redraw it every time, and that's fine, but you should have time on the exam to do so. It's going to look like this, where I have a 3, 2, and 6, and then a 2 and a 2. It's all 12 volts right there. And then I do the 3, 2, and the 6, and the 2 and the 2. The 3, 2, and the 6 is 12. The 2 and the 2 is 4. That's 12 volts. Let's see, can I? Yeah, I can tell the voltages right now. Like if I didn't ask you the equivalent capacitance, I could stop right here and tell you what the voltages are, because these numbers are a factor of 3 off. So I know that my voltage here is going to be 3 times my voltage here, and the two numbers have to add up equal to 12. So what numbers are 3 times apart and then have to add up equal to 12?
Oh, you get 12. It's supposed to be 11.
Oh, it's 11.
Because it's 3 plus 2.
Yeah. Okay. You're right. Well, that's not so easy then. So now I have to find the equivalent capacitance. 1 over 11 plus 1 over 4. And that is 2.9 microfarads. And so to find the voltage on each of those, I would say this is 2.9 microfarads with 12 volts, and then I want to know what is the charge on that. So I would say, and this is where I start stepping backwards, I say Q is equal to CV, 2.9 times 12, that's 35 microcoulombs. And then realize that this has 35 microcoulombs and this has 35 microcoulombs. And then I can find the voltage. V is equal to Q over C, 35 over 11. That's 3.2. So let's see, I'll do the voltages in green. 3.2 volts. And then this one has to be, what, 8.8 volts. How'd I get 8.8? I did 12 minus 3.2. So, or I could do 35 divided by 4. So those are my voltages. Now I'm really almost done. I have 3.2, 3.2, 3.2, 8.8, 8.8. Because those are in parallel, they have the same voltage. Then over here, these two capacitors right here, they share 8.8 volts. So that means I have 4.4 volts and 4.4 volts. And here I have 8.8 volts. And then these up here, I have 3.2 volts, 3.2 volts. And these two share 3.2 volts. They split it up between them. And I have to figure out what is the voltage on each of those. It's not trivial because the number doesn't split up evenly. But I can look back down here, which is the equivalent capacitor of that 3 and the 6. I figure out its charge, Q equals CV, or 6.4 microcoulombs. And then I realize that this has 6.4 microcoulombs, and this has 6.4 microcoulombs. With me? Yeah? William?
How did you get the, I understand the voltage, but how did you distribute it into 6.4?
Because this capacitor down here has 6.4 microcoulombs. Capacitors in series have the same charge, and they have the same charge as their equivalent capacitor. So 6.4 microcoulombs is also on this capacitor and that capacitor, because those two capacitors make up this 2 microfarad capacitor. Once I know the charge and the capacitance, I can find the voltage. I'll do it in magenta. V is Q over C. So that's 6.4 divided by 3. So 2.1 on this one. And then on the other one is going to be like 1.1. Is that right? Yeah, 1.1 volts on that one. In a similar way, 6.4 divided by 6. And then you're done. I mean, I would ask you, what is the charge or voltage? Honestly, if I gave you this question, I'd probably ask you the charge or voltage on one of these capacitors. Because those are the most embedded, those are the hardest, right? Like you really have to know everything in order to answer those questions. You can't fake it. You can't.
So 35 microcoulombs is like QE, Q?
This is the charge on the equivalent capacitor. But since they're in series, they have the same charge and the same charge as their equivalent capacitor.
I hate to ask this again, but I'm just trying to figure. I'm still trying. After practicing the past test, I'm still trying to narrow down how exactly to distribute voltage.
Okay. Well, when you have two capacitors in series and you want to distribute the voltage, you have to find the charge on the equivalent capacitor, just like we did up here. I found the charge that was on the equivalent capacitor, and once I know the charge and the capacitance of each capacitor, finding the voltage is a matter of V equals Q divided by C. Now, when the capacitors are the same, we just split it up in two, and you'll have some like that where you have identical capacitors. You can just split it into two parts. That's easy. And then also, when our capacitors are like a 3 and a 6, and we have 12 volts across it, then we don't really have to do all that business because we know how those voltages are distributed. If they're a factor of 2 apart, or if they're a factor of 3 apart. Okay? Yes? All right, we can come back to capacitor circuits for sure, but to ensure that we get through everything, let's look at some of the others. And by the way, you'll have some simpler capacitor circuits where I ask you what is the equivalent or what is the voltage. So knowing how to do this one will also help you to do some of the others. Let's look at a multi-loop circuit. I did a bunch last help session. But you'll have one of these like where what are the equations? I'll zoom it in just a second. Let me just find one that works. No equations. Okay, here we go. Number 7. This looks like I don't know what exam this is from, but it's on that handout that I gave you last week. So remember what I said, there are two ways that I can make this easier, a multi-loop circuit, is I can give you one of the currents from one of the branches, or I can leave off a resistor in one of the branches. So if I left this resistor off, then that makes it easier, because if I was looking for, say, I1, I would just take the big loop, and the equation for that big loop would not include I3, because there wouldn't be a resistor if I left off that 3 ohm resistor. But let's say, like this one, I would tell you what is the I would tell you what is I3, that it's 2 amps. And by the way that I would phrase this is I wouldn't give you directions. Like I wouldn't give you any of this. I won't give you any of that. And I would tell you not I3, but I would say the 2 amps is in the 3 ohm resistor. And I would say that it's down. That's all that I would say, is that the 3 ohm resistor has 2 amps in the downward direction. Not going to have any arrows on your circuit, no currents labeled. You have to do that yourself. So when you do that, you just say, well, I have I1, I have I2, and I have I3. Now you have to be careful that you get I3 in the downward direction, because I told you that's what that current is. And so that's important, that you get that current in the right direction if I tell you one of them. So make sure that you get that correct, okay? Y'all hear what I'm saying? That it is important when I give you the current and the direction that you label it correctly. Yes? All right. So now, if I want to know what I2 is, I2, the equation for I2 is found in the equation from the left loop and also from the right loop. I'm going to use the right loop, of course, because I know what I3 is. And so it's just an easier equation to solve. Let's start right here. I start anywhere, doesn't matter. And I'm going to travel in that direction. So I get minus 5 plus 1I2 minus 3I3 plus 12. And that's equal to 0. That's the loop rule. It's an application of the loop rule. Remember our rules that when I'm traveling from high to low potential, I get a negative change in potential. When I'm traveling against the current, I get a positive change in potential. When I'm going with the current, I get a negative change in potential. And when I'm going from low to high potential, I get a positive change in potential for that battery. Remember those 4 little rules that I told you when you're applying the loop rule. And in fact, in this one, all 4 come up. Okay? So you need to be prepared to write that equation correctly. That's where most of you, if you mess up, that's probably where you're going to mess up. But I'm hoping nobody will mess up. Really? You should not mess up this problem. Like the capacitor circuit and the combination circuit, that's a little more involved. But this problem, you should get this problem as a freebie almost, with just a little bit of practice. Right?
Without those F8s right there, how would I tell what is positive, what is negative?
Without the what?
Without the arrows, how do I?
You just draw the arrows, whatever you want, doesn't matter. Except for I3. If I tell you the direction of a current, you need to label it as I tell you.
And how do you tell whether it's positive or negative? Because what if you make up the traveling direction from left to right?
Doesn't matter what direction you travel. The only thing that matters is that you apply those rules correctly.
Refer to the red arrow.
Doesn't matter. I could go the other direction. I could go the other direction, in which case it would be minus 12 plus 3I3 minus 1I2 plus 5. It would just be the negative of this equation. Everything would be negated. Everything would be opposite. Plus 5 minus 1I2 plus 3I3 minus 12.
So essentially, whenever it's going to ask like multiple equations and which one fits it, I would just have to.
We'll look at some of those in just a minute. So let's finish this right now. So now I put in my current. I have 2 amps for I3. So I have minus 5 plus I2 minus 6 plus 12 equals 0. So I2 is equal to minus 11. 1 is equal to negative 1. So if I can get rid of B and D, oh, it's either up or down. I chose I2 to be down, so that means it's going to be up because it came out negative. What that negative means is, uh-oh, I chose the wrong direction. And I just choose the opposite of what I chose. That's number 2 on the free response. Number 3 is going to look, let's see, let's find one that's like it. It'll be a combination circuit. Yeah, Em?
So we use different colors on the response. Like,
Yeah, of course. Yeah.
just
Bring in
like,
your.
since it might be easier to like.
I agree.
And that number 7 that you just pulled up, which test is that?
Oh, I have no idea. It's on that handout that I gave you there with all the multi-loop circuits, and it looks like it's on page.
Is that the one
It's
that was-
early on. It's like
Is that the one that was looking up?
page 4. Yeah. It's an early exam. Those were that handout that I gave you is like every multi-loop circuit that I've ever done for exams. So you can find all those in the old exams, but I just collected them all in one spot. Number 25 is a good example here. I don't know which exam this is. This is S8, Spring 18. This is a good example of the third and fourth problems that you'll have. I'll have a circuit that'll be similar difficulty to this. It'll be different, right? Like it could have different series and parallel branches, but a similar thing. And you'll also have a fourth question, what is the voltage across one of the resistors? But I'll have it kind of like this, where the numbers work out nicely. I think this one works out nicely. Yeah, this one works out nicely. So if you get really bogged down in the numbers, then you probably went wrong somewhere. If you're starting to get a lot of long decimal numbers, you probably went wrong. That's not true on all the questions, but it'll be true on this one. Okay? Wait, is that true? I think that's true. The very final answer might be a fraction, but most of the numbers are going to come out even. So let's try this one. I start with this part and this part. A 2 and 4 in series, that's 6. A 3 and 6 in series is 2, and then I have a 1, so I have 6, 2, 1, 2. You probably already see a lot of where we're going because I have a 6 and a 3 in parallel. And so I'm just going to jump right ahead and say that I have a 2 and 2 in series. And so now you're sort of cheering a little bit on the inside because the numbers work out so that it's a little bit easier. Are you cheering just a little bit on the inside? Just a little bit. It'll be similar in difficulty. So if I have 12 volts, that means I have 6 volts and 6 volts. Two identical resistors, they split up that voltage identically. That means I have 6 volts here, I have 6 volts here, and across these two, I have 6 volts. Now, I can just say right off that this is 4 volts and 2 volts. And I just say that because I know they have to add up equal to 6. I know this one has twice the voltage of that one. And so 4 and 2 fit that bill. Those are the only numbers. We've seen that in a number of different examples. Or I could say I have a 3 ohm resistor with 6 volts. That means I have 2 amps going through this part of the circuit. 3 ohm resistor, 6 volts divided by 3 ohms equals 2 amps. So I have 2 amps going through those two resistors, and then I just do Ohm's law, V equals IR. 2 times 2 is 4, 1 times 2 is 2. And then, almost done, I think. Oh yeah, so if that's 4 volts, that means I have 4 volts here, 4 volts here, I have 2 volts here, I have 6 volts here, and then my last step is to split up the voltages on that 2 and 4 ohm resistor. Some of you might be able to tell me what is the voltage right off on the 2 ohm resistor. What do you think? No, you can do this. Well, what is my current through the 2 and the 4 ohm resistor? 2 and 4 is what equivalent? What's 2 plus 4? It's 6. So the 2 plus 4 up here has an equivalent of 6 ohms. I know that I have 6 volts across those combined, so they have a current of 1 amp. 6 divided by 6. So if I have 1 amp here and 1 amp here, that means I have 2 volts and 4 volts, which jives with what I would think should be true. That is that this voltage is half this voltage, and they should add up equal to 6. you have lots of little internal checks that you can do to make sure that you're doing the question right. And if none of those checks if they don't fit right, then you need to go back and just backtrack. It's like Sudoku, right? When you put the 8 in the wrong point in one of the squares, and then the other squares start not to work just quite right. It's similar here, where if you get one of the things wrong, it'll show up in some of your other answers. And then that's it. That's, you know.
Do you want us to label all the voltages and all the resistors, or just?
You don't have to. No, you don't have to, Landon, but it's a good practice, because then, like I said, if you got something wrong, you'll see it because the voltages won't add up correctly. I think you'll have plenty of time to do it. If you sort of know what you're doing, I think you'll have time, so it's a good practice to do so. I do want to see your work. So, yeah.
So how is the voltage distributed for resistors in series?
In a similar way, they have to add up, as they did for capacitors, they have to add up equal to the total voltage, right? 2 plus 4 is equal to 6. And in a similar way with capacitors, capacitors in series have the same charge, resistors in series have the same current. And so here, we figured out what was the current on each of these resistors, because we knew that we had a 6 ohm resistor with 6 volts across it. So I was equal to V over R, which is 1 amp. And so that's how I knew that I had 1 amp flowing through each of those resistors. And then I just do IR. 1 times 2, 1 times 4 gives me the voltages on each of those. But they have to always add up to equal the total voltage. That's questions 3 and 4.
Still very confusing, because you're trying to add up for like a 6 volt, and then you're trying to add up to 12 volts at the same time.
No. Don't get confused by this here, because we're breaking the circuit down into individual parts. And you have to make sure you step back consistently, because here we found that this circuit right here had 6 volts across it.
So the equivalent, this one was what?
The equivalent is 4 ohms. Yeah, so my final circuit down here, I didn't write it, did I? Is 2 plus 2 is 4 ohms. That's 12 volts. And then the voltage across R5 is 4 volts. Right, that is this voltage right here. But you don't have to solve the whole thing. But on your problem, you'll have to solve for most of it to get the one that I want. Because it's embedded. It's dependent upon all the other voltages. Alrighty? Let's sort of scroll through some of the old tests and see if you have any particular questions from the multiple choice, or if you want, we can do some more of these.
So, some of the questions on the concept test for getting out,
All right, let's take a look.
the power works.
Oh yeah, the power. There are a couple of power problems. What is that?
What do you have to worry, whenever it's talking about brightness?
Oh
I know
yeah.
I know you worry about power, but is it the current that you worry about, or is it the voltage that you worry about?
Which one? Where is it? Was it in the one that I posted online?
I know it should be in,
Chapter 3, right? Hmm?
Starts talking about brightness.
Yeah, I don't see it. Let me download it. Maybe out a different file on Moodle. All right, must be 4 then. Oh, here we go. Yeah, so here I have two light bulbs. Two of them are in parallel, and then two of them are in series. I want to know which one is brighter. Um, you can look at this in a couple different ways. So if I have two light bulbs in parallel, let's say I have 12 volts here. I know I have 12 volts here and 12 volts here. And then if I have two light bulbs in series, I know I have 6 volts here and 6 volts here. Now power is equal to V times I. These two on the left, these parallel, they have a bigger voltage, right? So they have a bigger voltage by a factor of 2. So I can put in a factor of 2 right there. But they also have a bigger current by a factor of 2 because they all have the same resistance, all of these resistors. And so my current is also bigger by a factor of 2. So this one on the left is going to have 4 times the power of the one on the right. An individual light bulb or an individual resistor have 4 times the power. So I could look at it in that way. I could also think about it. Remember we had several equations for power where I just have the two variables that are changing. The resistors are all constant in this, so the resistance doesn't change. So but my voltage is increased by a factor of 2 going from here over to here. And when I do that, I get a factor of 4. So the answer to your question is that both the voltage and the current matter because they both have different voltages and different currents, both of these. And I'll see that in this equation. But if you just consider the voltage in this one and don't consider the current, then you'll get the wrong answer. You put a 2 that has twice the power. Really, it has 4 times the power. You can circumvent that by just looking at this, where I just have two variables that are changing, P and V. And you know that the R is constant, and that's where that factor of 4 comes from. I don't like to use those extra equations. It's just sort of too many variables floating around my head. I just remember that voltage and current are both changing. But it's up to you. You know, some people like to use that other equation. Does that answer your question?
Yeah.
Yeah.
Well, it was more along the lines of the lower, and I kind of got it as I went through it, but the lower your resistance, the higher the current.
Yeah. So, what you're asking there is, if I have a circuit just with a single resistor, how did it go? I forget how I asked that question. Lower resistors or lower resistance produces more power. Because the current is greater. I is increased. If you think about this equation, P is equal to I squared R. See, if R is decreased by a factor of 2, then I is increased by a factor of 2. Right, V equals IR. We had our 3 equations for power. P is equal to VI, P is equal to V squared over R, and then P is equal to I squared R. They were just substitutions where we substituted Ohm's law into that first equation. And so here, if I have R, I'm going to double I, which will give me a factor of 2, twice the power, because I have 4 over 2. Yeah, we didn't spend much time on this, and so you're going to see some power, but it'll be more straightforward than this. I don't want to dwell on this kind of question for too long. It is important, but we didn't spend a whole lot of time on this. Okay? Okay, let's, is that okay, Ian?
Yeah.
Cool. All right. You're going to see one like number 27. It might not be voltage, it might be current, that sort of thing. You're going to see some simpler circuits where they're just plain parallel or plain series. You'll see a question like this. I think there's a question about conventional direction of current. Conventional direction of current is as protons would flow. Protons flow in this direction from high to low. Remember? Protons go in that direction from high to low. This is the high side, and so they roll down the hill to the low side. You're going to see some stuff about internal resistance. Don't forget your internal resistance. We have an equation for it that delta V, the terminal voltage, is E minus I times R. But really that's just an application of the loop rule, right? That if I have multiple resistors in a circuit, the sum of all the voltages around that circuit will equal to 0. As I said, you'll see one like 18. Nothing like this, nothing like 11. Pretty sure you see one with a layout similar to this. I don't know if it's resistors or capacitors, but I would worked on a question that was similar to it. I think it made the final cut. Y'all know how to do this, how to look at this? Some of you got confused about this on OpenSteps.
Just like redraw because that's like.
Yeah, so first of all, it throws people off because there's no battery. And so if you want to really throw in a battery, I just put a wire on A and a wire on B, and then that's my circuit again. And then the other thing, like you said, Lena, is just the layout of it is sort of wonky. And so it's going to look like this. They're all parallel, yeah. So I know that because as I come up here, I split into 3 branches. So here's the top branch, here's the middle branch, here's the bottom branch, and then I come back to the battery. You have that on an OpenStax question. I'm pretty sure either resistors or capacitors made its way on there. Okay? So be prepared for that. Make sure that you're not thrown off by it. You're going to see some stuff, I think it made the final cut, about voltmeters and ammeters. You're going to see basically everything, but voltmeters and ammeters, how they're hooked up, what their resistances are like. I'm pretty sure you see something like this.
Can you go over that?
Number 1?
No, the voltmeter there.
Yeah, so voltmeters, really just 2 facts you need to know about each. Voltmeters, ammeters. Voltmeters hooked up in parallel. Ammeters hooked up in series. Voltmeters have a big resistance. Ammeters have a small resistance. In both cases, neither the voltmeter nor the ammeter will affect the circuit very much. So for example, with a voltmeter, when I hook it up like this, because it has such a big resistance, thousands and thousands of ohms, it has such a big resistance that when my current comes along here, most of my current goes through there. And I just get like a little dribble of current that goes through my voltmeter, a tiny little bit, because the resistance is so big. That's why you hook it up in parallel. It doesn't impact the circuit very much when you hook it up in parallel. If you were to throw that voltmeter into the circuit right here, it's like it would stop most of the current because it has such a big resistance. You would change the resistance of the circuit so much. But when you put it in parallel, it doesn't really change the resistance of the circuit at all. Because remember, when you have resistors in parallel, the equivalent resistance is smaller than your smallest resistor. And when you have a really big resistor, then the equivalent resistance is basically equal to the smaller resistor. Because the big resistor is not really another path for electricity at all because it's so big. Electricity just can't go that direction. Now with the ammeter, when I hook up an ammeter, I put it in series. Because, you know, my current is coming along here, and you want that full current to go through the ammeter, and then you can measure what that current is. But because the ammeter has such a small resistance, just it's basically a piece of wire. If you ever look in the back of your ammeter, you just basically have a coil of wire. That's your shunt resistor you in the lab. And so while this sort of has a normal voltage, this just has a tiny little voltage. Hardly enough to affect the circuit at all. So that's why we have big and small resistors in our ammeters, and that's why we hook them up in parallel and series. Okay? So I say you really should know these two facts for each, but you also need to have some working knowledge of why they are set up like that. If you look back at some of them, well, this was pretty simple. This was just sort of knowing it, but the statements that are true here, the resistance of the voltmeter is big, an ammeter is connected in series. The voltage across an ammeter is small. That's always true. Oh, and this is always true. Yeah, so all of these are correct. What you got to be careful is sometimes, like, what if I said the voltage? No. What if I said the current across or through an ammeter is small? That can be true, but not necessarily true. The current is whatever you're measuring. Or if I said that the voltage across a voltmeter, what would I say, is big, that could be true. It is whatever it is across the resistor. Because you remember resistors in parallel, they have the same voltage. So whatever voltage is here is also here. The current through a voltmeter is always small. But the voltage across a voltmeter, it is whatever it is. It's big, it's small, it's whatever it is. Okay? One question. You know, there's a lot of one question topics on this test. Make sure you understand how to calculate the capacitance and how to just sort of think about how the variables are related to one another when you're looking at these two equations, Q equals CV and C equals, epsilon naught A over D. There's a kappa in there too. So for example here, I have a parallel plate capacitor, initially has a charge of 12 coulombs. And then the plates are moved to 3 times their original separation. So I'm increasing that by a factor of 3. So I'm decreasing the capacitance by a factor of a third. And what you want to be clear here is that the capacitor remains connected to the battery. That means that this value stays constant. And if I decrease this by a factor of a third, then this is going to decrease also by a factor of a third. So whereas it had 12 coulombs, now it's going to have 4 coulombs. The tricky part, is it tricky? It's tricky if you're not really familiar with it. The tricky part is to say, what's remaining constant, my voltage or my charge? The charge is constant when what? When you keep the capacitor hooked up to the battery or when you remove it from the battery? When is the charge constant? When you remove it. Yeah, that's right. When you remove the capacitor from the battery, because it's like the battery is the lifeblood for that capacitor. It feeds charge into the capacitor. But when you take the battery away, then the capacitor just sitting out there is like a bowl full of candy. It has the charge that it has, and that doesn't change. Now the voltage can change if you change the dimensions of the capacitor. Yeah.
Yeah, but regarding that equation, do we have to know what epsilon?
You have what's on the equation sheet. Epsilon naught is on the equation sheet.
Well, I'm referring to the 8.85 value.
Right, that's epsilon naught. That's on the equation sheet. Right?
Didn't we do this on the last?
Did you? Let's double check. Am I telling you wrong?
I don't know why I went.
I feel like it's me. Oh no, it's on Moodle, isn't it? I haven't put them on the website yet. We might have. I don't remember. Try to put it out of my memory. Nope, I don't think so. Oh wait, yeah. No, you're right. You're right. Oh shoot. Did I put it on the test? Huh? I might have put it on the test. I'll send you an email and tell you. You might have to do it again. Are you okay with that? Come on. Huh? You just plug it in.
I was just wondering why you were doing it.
Yeah, I'm pretty sure it made it on the test. I'll send you an email when I get back to my office. I have to look at the exam. I guess I just forgot or whatever. What? I'm sorry. We could have had more questions about other stuff. I'll send you an email. I'm not sure. I forget. I'll send you an email and tell you if those types of questions are on the exam. But you know how to do them, right? You know how to do them. Those are some of the easier questions. The harder questions are dealing with circuits. Like that's really. All right, let's see what we got. In particular, I can sort of scroll down through here. Let me know if there's anything that stands out to you. Are there any particular problems about OpenStacks? There are some questions straight from OpenStacks. So there are no graphing problems like this. Y'all should have done that in the lab. No. Scroll through OpenStacks right quick.
So a combination part on the free response, that's just reducing the circuit.
Yeah, finding the equivalent resistance, and then I'll also ask you what is the voltage. But reducing the circuit properly is a big part of it. I like to draw the intermediate steps. It will help you to think about the circuit more. We've worked through a lot of these. I mean, a lot of these questions are actually from last year's final. So these questions about, yeah? No? All right. And then there's the one other one. Oh, there's that one. No, folks? Is that all that you have for today?
Is there a question? Might have been on the very end. It's like a 3-part question. I think I'm gonna call it. Well, like it use like a sentence diagram.
Mm-hmm. Oh, this one? That's tripped up a lot of people.
Yeah,
Is that the one you want to? Yeah, let's look at it. It's a good question in the sense of it deals with EMF and internal resistance. So I don't know why people got tripped up on it, but I have a battery with a certain EMF. I have a voltmeter. That's going to be my voltmeter, and then I have an internal resistance. And I'm told that I have 1.585 volts. 1.585 volts. That's my EMF. It says the terminal voltage of a 1.58 alkaline cell. The internal resistance here is 0.1 ohms, and I'm using a 1,000 ohm voltmeter. Isn't that what it told me? Yeah, I place a 1,000 ohm. And the first question, there were a couple questions. One just asked the current. One asked the terminal voltage. When you ask the terminal voltage, you have to realize that this is my battery. That's my battery. Here's my terminals. The terminal voltage is whatever voltage is right here. This is your voltage across the terminals. The battery has an internal resistance. And the terminal voltage is not going to be more or equal to 1.585. It's going to be something less. But your first step was to find the current. I is V over R. That's going to be equal to 1.585 divided by 1,000.1. And then it was like 1.5848 or something. And then it asks you what is the terminal voltage. Well, once you find that current, this voltage is equal to I times R. You have to keep more sig figs than you need because the terminal voltage in this case is really, really close to this. I think it was 1.5848. It was just a little bit smaller because you had a little potential drop across this internal resistor. But when I give you a internal resistance problem, I'll make the resistor of the internal resistor bigger. It just makes the math a little easier. The sig figs don't come important anymore. Okay? Is that clear? It's not, I know it looks a little bit different, but it's really not different than any of the other series circuits. You just have to understand the language. So I know it's difficult. Yeah.
Have we covered multi-loop circuits yet?
Uh-huh. Yeah, we did it very good.
Oh, what's that 12-volt one?
The 12-volt one.
The one that involved the 12-volt battery.
Maybe, I don't know.
Multiple capacitors.
Oh yeah, that's not a multi-loop circuit. Yeah, we did that one. All right. Any other questions, Joe? It's almost 4. No? All right, make sure I get your names before you go, okay? I'll be around for a little bit longer.